Welcome. My name is Sam Houston and I'm with ATEC Training. Today we're going to be discussing all things electric vehicles. We're going to be using our electric vehicle systems trainer, model 5820, and our vehicle technology trainer, model 610N. Both of these units are going to allow you and your students to have an immersive electric vehicle experience. But before we get started, let's look at a few safety precautions. ATEC Training believes that safety should be your #1 priority. And before we get started on going over how to work on some electric vehicle systems and components, we want to cover some basic safety information with you. Electric vehicle manufacturers may choose to limit the required use of personal protective equipment by any technician while servicing the vehicle. They do that because they may choose to rely on the integration of safety systems in the vehicle that will ensure the high voltage components are de-energized by using a scan tool or other electronic means. As the technician or the instructor, you must refer to the employer's or the OEM's specific guidelines, procedures, and training when selecting the appropriate and recommended personal protective equipment. Remember, it is your job to be trained and certified prior to servicing these vehicles. Hybrid electric vehicles and electric vehicles both contain high voltage batteries. There is the risk of electric shock, electric leakage, or similar accidents if the high voltage components and the vehicle are handled incorrectly. Be sure to follow the correct work procedures when performing inspection and maintenance. And a few additional tips that we also insist on is that you need to be sure to wear your insulative protective equipment that consists of either gloves and/or shoes, face shield, and safety glasses before beginning any work on any high voltage system. Again, refer to your repair manual for the specifics. You want to make sure also that you clearly identify the persons responsible for the high voltage work and ensure that other persons in the area are not able to touch the vehicle. And when you're not working on the car, make sure you cover up all the high voltage parts with an insulating cover sheet or similar item to prevent other persons from contacting them. Make sure to do all your safety checks first. Make sure your safety PPE is on. Make sure your vehicle is powered down. Make sure all your labels are correct and your vehicle is properly blocked off. And if you follow these simple steps, it'll help increase your safety while working on electric vehicles. Whether you are a new student just getting into the EV game or a seasoned instructor looking to add electric vehicle training to your current platform, there are a few basic approaches that ATEC recommends. One is we have to start, just like any other subject, we have to start explaining the basics, system basics of how these systems are developed. So if you're talking electric vehicles, you want to break everything down into small bite-sized pieces and concepts that are easy for you and for your students to understand. And to take that to the next level, you're going to want to apply the knowledge directly to the vehicle and bring yourself and your students out to the vehicle and identify exactly where these systems and components exist and live on the training vehicle within your fleet. Once you've done that, then you're going to want to begin the process of analyzing the data that's available for those specific systems. This might include some information that's available in the repair manual and also using a scan tool to look at live data and active testing. And then once you've got a good feel for how all the systems are integrated and brought together, that's going to allow you to open that door up for doing some troubleshooting and some additional testing on the vehicle to determine root cause of failure. It's through these systems and this process that you're going to be able to develop out a better understanding of the electric vehicle and how it works and how to become a better troubleshooter using the systems. So with that being said, let's start the process off and let's break this thing down piece by piece. Pictured on your screen is a traditional topology map that we might find in any vehicle or any make or model in the repair manual. This particular topology map is an outline of our 5820 electric vehicle systems trainer. This unit is designed to give you all the common pieces that will be found within most of the manufacturers that are out there. But if you are like my students, or like I was when I was a technician, these maps can be very difficult to follow along with, and they don't necessarily provide us all the information necessary to have a further understanding of how the systems are integrated, or really even what they actually do. So at ATech, we've taken this topology and we've broken this down into a format that is easy for you and your students to understand. When we look at each individual system separately, it becomes less intimidating and easier for us to understand the ins and outs of how that unit works. Our electric vehicle systems trainer does include a high voltage battery charging station, like a level 1 that plugs within the wall. It also includes a charge contactor, a high voltage fuse, a high voltage battery, keeping in mind that it's a 24-volt battery, so that way it's safe to use without any additional personal protective equipment. We also have a high voltage contactor, a high voltage junction block, and then on the other side in the red, you're going to see our low voltage junction block, our low voltage fuse, our low voltage control, which includes our ignition switch and our simulated body electrical circuits. Of course, a low voltage battery and a low voltage battery charger. And we do also have our two key components here, is our DC to DC converter and our DC to AC inverter, which ultimately is going to drive our AC traction motor. Now, this is easy to say and look over and say, hey, all these parts and pieces work together, but it's harder to actually visualize what that looks like. So we're going to go ahead and do some assembly on our trainer board, and this type of activity you can do directly with your students to help them understand how these systems integrate better together. To develop a student or technician's further understanding of the topology map we just looked at, ATech has made the 5820 electric vehicle system trainer and piece by piece to help you have a better understanding. Let's have a look at some different parts that we can put on our board. Part number 1 I've got here is our high voltage battery pack. This is a nickel metal hydride battery pack. It's going to have a feel-good monitor on top so you can see what your state of charge is. And again, 24 volts, so we've got it in blue, but you don't need any special PPE in order to use this high voltage battery. On the opposing side of this, we have our low voltage battery here, 12 volts, nickel metal hydride, and again, it still has the state of charge monitor on the top, so that way you and your students can see how much battery charge and life you have left. In order to start bringing all of our wiring together, our students are very used to seeing low voltage junction blocks, where we might bring in, all of our hot and all of our ground wires together. But in order to be safe, we want to make sure that we circuit protect everything. So we've got our low voltage circuit protection as well. And up here on the top, we're going to have our control board. This board's going to include our ready up switch, so that way we can drive the vehicle down the road, as well as our simulated body electrical, including our headlights and tail and brake light assemblies. Now, in order to charge our low voltage battery, we've got to have some sort of charging system. We cannot just hook our high voltage battery up directly to our low voltage battery. We need some sort of intermediary between the two. That is where our low voltage battery charger comes into play. It's going to allow us to take power out of our battery and charge our low voltage battery, but we must have another component in between these two. This is where our DC to DC conversion comes in. That's because we cannot take high voltage coming out of our battery or our traction battery pack and directly apply it to our smart battery controller, otherwise it's just going to fizzle out. We must take our 24 volts and step it down to about 12 volts in order for our battery management system to effectively charge our 12 volt battery here. From this point, we can look at our high voltage control circuits. So we have our high voltage contactor. This unit is controlled via the ready up button. So when you as the end user make the command for the vehicle to ready up, it will activate the high voltage contactor, which will again supply power directly out of the high voltage battery into our DC to AC inverter. Then our DC to AC inverter is going to convert that high voltage direct current electricity into a single phase 120 volt at 60 hertz, AC or alternating current. These are your core components. However, we cannot just drive this vehicle for infinity, and there's no gas tank to put gas in this, so we have to charge up our high voltage battery. To protect our high voltage system, we've got our quick burn ceramic fuse. We also have our high voltage junction block. It's going to allow us to bring all of our independent power and our independent grounds. This is a hybrid electric, and electric vehicles run both a redundant ground system and a power supply system that are separate from chassis ground. And then we're going to add one more contactor to the mix. This is going to be our charge contactor. This is going to allow us to take our 120 volt DC adapter or our level 1 wall charger and plug directly in. And when we do that, that's going to activate this charge contactor, which will isolate out the entire system. So we're only using the level 1 charger to charge up the high voltage battery pack. And this is the parts and pieces that make up the majority of basic electric vehicle systems that are out there. Now that your students have had a chance to get hands-on and start assembling the pieces, let's wire this thing up and see how it operates. Now that we have our trainer completely wired up, let's take a look at a few operations. First of all, our ready up switch is right here. So when I click this switch on, it's going to use our 12 volt system. It's going to activate our high voltage contactor, which is going to bring alive all of our high voltage systems. So our high voltage battery is passing power through the HV circuit protection, sharing that power in the junction block, and then from the junction block it's being divided up to the DC to DC converter, and then over here to the DC to AC inverter. So we've got high voltage coming in, 120 volt AC coming out. We also see down here our conversions happening. We're running about 26 volts in our high voltage battery pack. We're stepping that down to just under 12 volts. That's a safe voltage for our smart battery management system. And then this unit, as we see, it's red here, which means it's detected that our low voltage battery has a lower state of charge than what it wants to see. It's looking pretty good on our scale. This thing is top notch here. It's going to fill this battery all the way up. If we look over here on our low voltage side, we have our simulated body circuits. Our tail lights are on, our headlights are on. Everything is protected by a simple blade fuse here. And we do have our junction block that's allowing us to spread our power out so we can supply power to our high voltage contactor. If we notice up here in the top left hand corner, this is our charge contactor assembly. And this unit is designed to separate out or isolate the entire system just so it can charge the high voltage battery. So if we were bringing this vehicle into the garage, I would turn the vehicle off. I would go out to my level 1 charger, which is running at 120 volts, and I'm going to plug my charger into the wall. And then I'm going to take my umbilical cord and I'm going to plug that directly into the battery charging port on the trainer. And then I would plug this directly into the wall. And when I do that, this LED light will come on to let me know the state of charge. When it's red, that means the unit needs to be charged up. When it turns solid green, then that means the unit is completely charged and ready to be driven down the road. So our charge contactor works very similar to an actual electric vehicle in that it's going to isolate the car out so the vehicle cannot be driven while it's plugged into the wall. This is very, very important. Everybody may have seen someone drive down the road with the gas pump hose hanging and dangling out of the side of the car. We certainly cannot do that when we're hooked up to our house power or to a fast charge station somewhere out on our commute. So now we've had a chance to see how the charge contactor and the level 1 chargers works on our trainer here. Let's go over to our electric vehicle and see how it actually works on the car itself. In our lab today, we have a 2013 Nissan Leaf. We're going to be using this vehicle to do some hands-on activities. We looked at our previous trainer, our 5820, and learned how the wall charging works on it. And now we're going to bring ourselves and our students on out to the shop and show them exactly how the wall charging process works. We have to remember, it might seem simple, but a lot of people have never been exposed to EV cars or an EV plug. Now, this is a great time to talk to your students about the 3 different types of charging stations that are out there. They're typically referred to as level 1, level 2, and level 3. To keep it simple, level 1 is going to be a lot like this guy. It runs off of 120 volts, and it takes quite a while to charge your EV vehicle up from ground zero to full charge. A level 2 is also available at home, but it's going to step it up and run off of about 220. So you're going to have an electrician most likely come in and wire that unit up for your house so you can charge your car in your garage. A level 3 charger is what we might find down at the supermarket or at a hotel or at any of the major stations that offer charging across the US. That's going to be a higher level charger. It's going to be running at about 400 plus volts that are going to be utilized for that type of unit. For today's example though, we're just going to use the trickle charge feature. We're just going to use our simple 120. It comes with the car, and we're going to learn how to plug this thing in. The first step is in the driver's seat. There's a little button, and it actually has a little gas can icon on it with a little lightning bolt above it to let you know that that's where you're going to press that button, and it's going to open up this charge port lid here in the front. Once this charge port lid is open here in the front, you're going to reach down inside and you're going to find 2 ports in there. One port's going to have an orange color. That's for your level 1 and level 2 chargers. The other port on the left is much larger. That's going to be for your fast chargers. So once you reach inside, there's a little clip. You press the button, and the door slides open to allow you to insert the charger. You're going to remove the safety plug from the front of this charger, and we're going to slide this right on in until it clicks. Once it clicks, we're going to hear some active beeps. That's going to let us know that the charger is connected and the process begin. This particular model also has 3 indicator lights up in the dash, which most EV or partial EV vehicles have. I call it the feel-good monitor, but it's basically a state of charge indicator for you as far as your lights go. Now, just like in our trainer, the 5820, when this vehicle is hooked up to this charger and we're plugged in right here, the computer already knows that we are tied in and when the charging process has started and will not allow us to ready up this vehicle or to put it in gear and drive it away. That's a very safe feature, but definitely something that you're going to want to let your students know or your technicians know, that if there's a malfunction with the lid or with the charge port, that could potentially keep the vehicle from readying up. So one thing that we always face is that what we used to call a no start. Now we're going to be faced with a lot of no ready up issues. And it's important that you explain to your students that there are a lot of integrated systems that have to work together in order to get the computer to give the thumbs up for the charging process to work. The best place to start with that is going to be utilizing your training vehicle in your lab and the repair manual information available for you. To help your students get a better understanding about how to diagnose and troubleshoot charging concerns or a no charge or a no ready up concern, it's very important that you give them a lot of exposure to data list information. So you'll see here on the screen, we've got our scan tool hooked up. We are on the onboard charger parameter data. I've done a custom list here just to show the pulse width modulation, signal voltage, and the EV state judgment. And what you're going to want your students to do is do this exercise, pull these data parameter points up, and have them actually plug the vehicle in. So when I plug the vehicle in, we're going to notice a couple different things are going to happen here on our scan tool. We're going to be able to see, we hear the beep for it to connect. We see our state judgment go to connected. That's very important. If that never goes to connected, it's very possible that there could be some mechanical or electrical malfunction in the switch in the charge port. And then if we also look on the left side, we'll see the pulse width modulation signal voltage. That number went up substantially to about 8.7 volts. That's giving us a good indicator using our scan tool that our wall charger is actually working. So if we were trying to figure out, it's always what comes first, the chicken or the egg. If we're trying to decide whether our charge cable is bad or our charge port or our control system, these are two excellent data parameters that you and your students can look at to verify that these systems are working properly. Now let's go back to our trainer board and look at our next component. Now we're back to our electric vehicle system trainer. You'll notice we've removed all the components except for the high voltage junction block and the low voltage junction block. Both of these units exist in a different variety of formats depending on what type of vehicle you're working on. Our Nissan Leaf, the high voltage junction block, is located inside of the battery pack itself, and the low voltage junction block can be found underneath the dash and underneath the hood. These units are varied in different locations, and you might even have an external high voltage junction block if you're working on an electric vehicle that's been converted, maybe like a classic car that's been converted over to electricity. We often find these high voltage junction blocks exterior of the battery pack assembly itself. It's important to have the conversation with your students that we have traditional 12-volt circuitry. It's going to run power and ground, and then our ground will be run back through the chassis of the vehicle. On our high voltage side though, we need to make sure our students understand that both the positive and the negative side of all the high voltage wiring are going to be colored in an orange color, and that the negative side of the high voltage system does not run through the chassis ground. This is done for circuit integrity checks, and it ultimately leads to a safer operation for the user of the vehicle. We're going to go ahead and take a look at the low voltage junction block inside the Nissan Leaf, and we're going to talk a little bit more about the high voltage junction block, because on this particular model it's built into the floor pan of the car, and we're most likely not going to be able to get it closer to it. Now we're back under the hood of our 2013 Nissan Leaf. This is ATEC's vehicle technology trainer, and as you'll notice, we've labeled most of the major components under the hood here using orange labels to aid your students identifying the differences or things that might exist on an EV car that they may not traditionally be used to seeing on a vehicle they have or one that they've worked on previously. Over here on the left, we're going to see a relay box. We've got a multitude of different relays in there. Coming over here to the driver's side, we're going to see our main fuse box. And over here, we've got our MC relay box. So let's pop the cover on these and have a look on the inside. Underneath our fuse cover, we're going to find low voltage and low current and high current fuses, things that are going to control stuff like the horn, the radio, the daytime running lights, your stop lamp, and also all the power feed circuit protection for most of your relays. If we look underneath our MC relay box right here, get the lid off of it. All right. There we go. Underneath it here, we've got our reverse lamp, our anti-theft horn, our MC relay, and our daytime running lights, our second relay for controlling those. So it's important to show your students that there are multiple areas available underneath the hood for power feed checks and relay checks. And these can be different locations what they might be used to seeing. So it's important to give them a chance to come out and look under the hood and identify where all these relay and junction blocks exist in the vehicle itself. Now let's skip over to the repair manual and have a look at some information about the high voltage junction block. I have a repair manual schematic pulled up here, giving us a shadowed image of the vehicle and the battery pack. As I mentioned before, all the high voltage battery cells and a lot of the battery management components do exist inside the pack that's underneath the car. So therefore, we're going to use some of these drawings to help us identify where certain pieces are. So labeled as number 1 is going to be our entire lithium ion battery pack. Number 2 is going to be our service grip plug. That way we can disconnect the vehicle from the high voltage battery system. Our main focus though for this is going to be down here on the second image, and we're going to be able to identify the battery junction box as number 4. So number 4 right here, you can see in this area, this is where your battery junction block is going to happen. This is where we're going to be tying in all of the high voltage cabling from all the different cell stacks and all the major components that need high voltage power fed to them. To take a closer look at the junction block itself, It is a smaller unit that's bolted inside the battery pack, and it is a very important unit here as it states below the junction block. It does include the system main relay, it includes the pre-charge relay, and it also does some communication with the vehicle control module to determine if there's any problems with any of the circuits. So our high voltage junction block is a very, very important part of the EV system, and it's great to give your students some exposure to these new and unique components that are special to EV cars. We have on display a couple different types of circuit protection that would be found on today's electric vehicles. On the right hand side, we have our low voltage circuit protection. It's a typical blade fuse that we would find on any car or vehicle, or basically anything that's running electrical circuits in it today. And we could test this unit just like we would on our traditional cars or other electrical training. We can go right to the top. We can test either test point to show continuity between the fuse. If this was actually in the vehicle, we could do voltage drop over those 2 points or available voltage on either side. That way we can ensure that the low voltage circuit protection is in good shape and its integrity is good. On the other side, we have our high voltage circuit protection. These are typically ceramic based fuses that are fast blowing, kind of similar to what we might find inside of our multimeter. These are located on cars, depending on the manufacturer, in a wide variety of different areas. They can be found inside the service grip plug, they can be inside the battery pack itself, or they could be inside of a computer that controls the battery pack. It really just depends on the manufacturer, so you're going to want to reference the factory repair manual before seeking out where and how to remove those fuses. To check these fuses, most repair manuals do have simple instructions for just doing the same type of resistance check across the fuse. And if we noticed here from one side to the other, our meter is saying OL, showing OLs, meaning that this fuse does not have any continuity between it. So if we were to take this fuse out, get us another fuse and replace it, and then we could recheck to verify that our repair has been made correctly. We can go right back on that fuse and notice that we now have continuity, so that fuse is in good shape. Well, when would we obviously, if we have low voltage circuit fuse problems, we most likely have either a component that is overdrawing the current, or we have a wire that is shorted to ground. A high voltage protection fuse typically only blows when there's been some sort of collision. So if you've got cars coming in from the body shop, or cars that have run over things on the road, or had any sort of undercarriage contact where there might have been some integrity of the floor wire compromised, those type of situations can blow the high voltage protection fuse. So if you have a car that comes into the shop and it is completely powered down, showing no signs of life whatsoever coming out of the battery pack, it might be a good idea to go ahead and look into the high voltage circuit protection and ensure that your fuses are in good shape. Now let's go over and take a look at the car, and we'll check out a few different circuit protection devices on the vehicle. Now we're back working on our Nissan Leaf. We're going to look at some low voltage circuit protection and doing some troubleshooting here to determine if our fuses are good. It's important that you talk to your students about all the different fuse locations. I know I've already mentioned that before, but it's really, really important. When we test low voltage fuses, it's just like we do on any other car. If the circuit is live, we can take our negative lead and put it on our negative battery cable, bring our positive lead over, and we're just going to look for available voltage on either side of our fuse. And if the fuse is in good shape, we should see the same amount of source voltage on either side of the fuse. It looks like these three fuses here are all in great shape. Now you do want to keep in mind though that there are other areas where fuses are located. There's another small fuse panel inside the car. On the battery cable itself, on the positive battery cable, are all 5 or 6 of your high current fuses. So these would be like 50, 60, 70, 80, 90, and 100 amp fuses. Not to be confused with the high voltage fuses for the lithium ion battery pack, but these are going to be your heavy current fuses. They're going to feed any electric motors or anything like that that's operating inside the vehicle itself. And then also over here on this side, we have the IPDM module as well. And if you flip the IPDM module over, you will also find that there are a series of fuses and relays underneath of this module as well. So most internal combustion engine cars don't hide the fuse boxes and the circuit protection, much like these EV cars do. They're kind of scattered throughout the entire vehicle. So I think it's good practice to send your students out and let them do some fuse testing on the vehicle itself. Since the high voltage fuse protection is located inside the battery pack of this vehicle, we're not going to be able to disassemble that for today's presentation, but we can look at a few more diagrams in the repair manual. So let's take a look at that now. Referring back to the repair manual, because we cannot drop the battery out of this car, we're on about step 15 of the battery disassembly. Now keep in mind there was a whole section on how to pull the battery out of the car, but we're about step 15 or 16 of disassembling the battery pack. And what we're seeing right here pictured is the top where you would put your service plug in. It would plug in right here, and then the case of the battery would be all around the exterior. So you've had to remove the entire case, split the shell open. There's a bunch of bus bars and wiring harnesses you have to remove. Then there's these 4 bolts that you have to remove, and then you flip this entire cover over. We'll see the picture here on the next screen. And when we flip this entire side over, what we're going to see here is the wiring connection for the PTC heater for the battery pack, as well as the output wire for the high voltage. And right here in the center, this is going to be our high voltage fuse for the Nissan Leaf. So trying to do the best we can to give everyone an example of where this fuse is located. It is not an easy process to get down to it, and you're really going to want to make sure that you've eliminated all other possibilities for what's causing your customer concern prior to going into this route. Let's take a moment to talk about contactor and contactor control. Contactor is just a fancy name for a relay. We've had this concept of contactors available in our industrial areas for many years, but we've only just seen it come about in modern vehicles since the onset of hybrid electric or full electric vehicle systems. Really, the only difference between a contactor and a relay is the amount of voltage it's capable of handling. We have some simulated contactors available on our electric vehicle systems trainer. I'm going to give you a basic rundown of how it works. So I've got a small amount of current. This would be my low voltage. I've got a switch to control. If we want to think about this as my ignition switch right here, and I'm just feeding power into one side of the coil and ground to the other side of the coil. And once we energize the coil, it will create an electromagnetic field that'll close the contact between the high and the low side junction block over here. What you really want to convey off to your students is that there are a lot of different control features when it comes to an electric vehicle. We have to turn circuits on or off in a wide variety of ways. Contactors control a large amount of current at a large amount of voltage. And when we bring both of those units together, if I have voltage on this side and no voltage on this side, I'm going to get an excessive amount of arc. Now, I did do a live demonstration of this in a previous video, and we're going to go ahead and insert that clip now. One of my favorite instructor-led demonstrations that I like to use when talking to my students about contactor circuits and pre-charge circuitry is I like to explain to them in a real-world fashion about what happens when you bring high amounts of voltage and high amounts of current together in any given environment. And the best way to do that is to use a set of jumper cables and a simple fully charged lead-acid battery and explain to your students that, hey, when I bridge an open in between 2 wires, one that's leading to a path to ground and one that's positive, this is what happens inside the relay or contactor. Okay, so we get a lot of arcing, we get some smoke coming off here, we got a lot of heat generated, and the reason why we have to have that pre-charge relay built into the contactor is so we can supply voltage to the ground side as well as have the voltage on the power side, so that way when we bring both of these units together, there's not a difference of voltage from either side. And when we do that, we don't get that arcing, we don't get that heat buildup, and we don't get that smoke that comes out through the process of bringing 2 high current, high voltage wires together. So as you saw in the previous demonstration, when you bring lots of current and lots of voltage together, a lot of sparks are emitted, a lot of heat is generated, and we use contactor control and a wide variety of relays to help prevent that from happening. On this particular setup here, when I energize the coil, we notice here we can see on the meter, now I have continuity between these two pins here. On an actual EV vehicle though, we're going to need to bring power to the positive side and power over to the other side of the contact in order to prevent that arcing from happening. This typically happens what we call our pre-charge relay. So let's go look at a pre-charge relay circuit on the wiring diagram. Let's look at some items on this diagram. We've got our high voltage power supply control diagram pulled up from our repair manual. We have different types of contactors available on the screen. We have what they call system main relay 1, which is going to be controlling the B+ side of the lithium ion battery pack. And we have system main relay 2, which is going to be controlling the negative side of the lithium ion battery pack. And then if we look up here at the top, we have our pre-charge relay. The one thing that we're kind of missing on the screen, if we follow down where it says out to high voltage system, there typically is a set of capacitors that is attached to this on the other side of this diagram. If we were to not have the pre-charge relay and just focus here on system main relay 1, if we close system main relay 2 as shown here in the diagram and just close system main relay number 1, we're going to get all that arc flash, that heavy damage from the voltage jumping across open airspace, heat, smoke, lots of bad things that we don't want to have happen inside the car. So what we need to do is we need to bring the high voltage power from the battery stack to the other side of the circuit. And the way we do that is with the pre-charge relay. So the VCM supplies power to the coil side of the pre-charge relay once we command the vehicle to ready up. That closes the pre-charge relay, and if you'll notice, it's tapped in right here. It's going to go across the pre-charge relay resistor. That's going to drop down a lot of the you're going to have a lot of voltage drop over that, and then it's going to slowly charge up the capacitor on the other side of this. Once that capacitor has reached complete charge, then the VCM will then command system main relay to come on, and when system main relay, at that point, when it makes the contact between these 2 points, we won't have arc flash here because we will have the same amount of current and voltage available on this side as we would have on this side. So that is why we need a pre-charge relay setup for most of our electric vehicles, and then also our hybrid electric vehicles operate in a very similar manner as well. Now let's move over to the vehicle and let's look at some data list points on these system main relays, pre-charge relays, or these contactors. We're looking at a live stream from our 2013 Nissan Leaf. I've got the EV HV vehicle control section pulled up, and I made a custom data list to include all the different types of contactors or control relays that we would find on most of our electric vehicles. A couple things I want to point out is on the right side of the screen, there are 3 active monitor data points that all say OK. I want to preference that almost all of these relays and systems are heavily monitored by the computer. This Nissan's monitoring it via the VCM, and they're looking for circuit integrity and operation. And anytime there's a failure, there's most likely going to be a code set beyond that. But as a technician, you're going to want to be able to look at the data to see if all of these units are actually coming on or off. It is almost impossible for things like the main relay positive and the main relay negative. These things are buried inside the battery pack, and they are large units that you're not going to be able to test with a traditional digital volt and ohm meter. So your best means of ensuring they're working properly is to look at them on the data list themselves. Before we activate the car and turn the ignition on, I'm going to go over what we're looking at here. So at the top we have the MC relay. That's the motor control relay, and it supplies the power to the EV system. The vehicle control module activates the motor control relay, and when it's activated, it supplies power to the EV system whenever the EV system needs to start. So basically the MC relay is going to be one of the very first relays we're going to see come on. Moving down from the left-hand side, we've got the HVN main relay. That is going to be your system main relay number 2. Again, this main relay number 2 is integrated into the battery pack, and it is also controlled by the VCM. And the system main relay 2 connects and disconnects the high voltage circuit side on the negative to the lithium ion battery. Underneath of that, we're going to have the FS relay, and the FS relay is going to be the fail-safe relay, and it supplies the driving power for the system main relay inside the lithium ion battery. So let's go back there. So the FS relay supplies the driving power for the system main relay. So if you need to deactivate the system main relay in an emergency, you would activate the fail-safe relay, and that's going to shut everything down. So fail-safe relays are an integral part of all EV circuits, so you're definitely going to want to learn more about them. Underneath that, we have the HVP main relay. That's going to be system main relay number 1, and it just controls the positive side of the lithium ion battery pack. Underneath of that, we've got the AC relay, and that's exactly what you think it is. That's the relay for the AC clutch. And then underneath that, we've got that HV pre-charge relay, and that's the relay that we spend a lot of time on in the wiring diagram looking at. So the HV pre-charge relay, it is a relay that's also integrated into the lithium ion battery, and is also controlled by the VCM. And so when the vehicle needs high voltage, or when high voltage power is required, the computer activates the pre-charge relay before activating the system main relay to prevent abrupt application of high voltage. So now we're going to go ahead and we're going to just press the ignition key on the vehicle, and we're going to watch the data list change. And then we're going to go ahead and we're going to put our foot on the brake pedal, and then we're going to press the button again to go ahead and ready up. And then once we ready up, we're going to see the pre-charge relay comes on really fast and back off. And then you see both the main relays come on, the MC relay came on. So these are tasks that you're going to want to share with your students and let them go through this process so they can monitor how the relays are coming on and in what order, so that way they have experience when they go out into the field in the event that they run into something that that they're not familiar with, or they've got a customer concern, that they've already got some experience pulling the relays up that are part of the electric vehicle control and monitoring them for coming on or off, in lieu of trying to take a traditional digital volt and ohm meter to do any testing on them. Now that we've had a chance to look at that, let's go under the hood and we're going to look at the MC relay up close. I've brought everyone back underneath the hood to kind of show you what type of relays you can actually put your hands on. Things like system main relay number 1, system main relay number 2, and the pre-charge relay. Those are all integrated into the battery pack, which on this particular vehicle is part of the underbelly of the car. But there are other control relays that we can get access to. Directly underneath the hood, we have our motor control relay. So if we pull the lid off this cover, we can see this relay is right here. And this relay can be tested. Obviously, we can use the scan tool like I just showed you, but you can also use a traditional automotive relay tester to test the coil side, to test the contact side, to make sure the relay is performing as it's supposed to. Other relays that you can find, there are also fail-safe relays, fail-safe charge relays. Those are also found in additional relay boxes underneath the hood. Now that we've gained a greater understanding of contactor control, let's take a look at another dynamic piece of the electric vehicle system. We've been talking earlier in previous segments about all the high voltage and how we can plug into the wall to charge our high voltage battery, but we haven't really talked about how do we generate power to charge our low voltage system. It would be nice if we could just take a wire straight from our high voltage battery pack and touch it over to our low voltage side, but unfortunately that's not how it works. We have to step down the power that comes out of the lithium ion battery pack step it down to a more palatable level so that way a smart battery management computer can control the amount of current and voltage applied to the low side circuit here. So the way this works on our electric board is we go to our ready up switch and we ready our car on, and we see our body electrical circuit comes on. When we do that, that activates the high voltage contactor, which goes ahead and supplies power from the high voltage battery pack to anything that needs it via the junction block. Right now I only have the DC to DC converter hooked up here in the middle. ATEC was very gracious enough to include 2 built-in voltmeters so we can visually see what's actually happening inside this DC to DC converter. As we can see, our high voltage battery pack is supplying just under 26 volts of power. The converter itself is stepping that down to 11.8. So 11.8 is going to be a much more palatable power source for our smart battery management system. This 11.8 will power up the battery management system, which will again charge our low voltage battery system here. So we can see if our battery monitor that is trying to charge it all the way up to the top. Most of your DC to DC conversion is happening inside of the vehicle itself. Most of these units are built into the power delivery module or directly into the traction motor assembly itself. But depending on the manufacturer and what accessories you have, you might find DC to DC conversion happening elsewhere, potentially in the air conditioning system, maybe the electric power steering system, or other additional systems, but it really just depends on who manufactured your electric vehicle. Now let's take a moment to look at some data points that we can see for DC to DC conversion on our Nissan Leaf. Now we're back to the data list for the 2013 Nissan Leaf. I've got 3 points pulled up from the EV HV vehicle controls menu. Right now we're looking at DC to DC converter status. This is a 0 or 1 PID data, 0 meaning that it's off, 1 meaning that it's on. And then we also have the DC to DC converter stat, which basically is going to tell us whether or not the vehicle is actually commanding the DC to DC converter to come on. And I've also included the 12 volt battery voltage because the main focus on the Leaf for DC to DC conversion is charging up that 12 volt battery. So we can see right now we're running about 12.32 volts or 12,320 millivolts. We're going to go ahead and put our foot on the brake pedal and press the red ignition button, and what we're going to see happen here is our converter status is going to change to on. And then our other status is going to change from 0 to 1 to let us know that that's actually working. And then we can immediately see that 12 volt battery voltage spike up 14.2, 14.4. And that's showing us as the technician that the DC to DC converter is, the command is working for it, that the DC to DC converter is actually working, and that the 12 volt battery is actually charging here. So these are great data points to go over with your students, and I definitely recommend you send them out and have them look at this information on an electric vehicle in your training facility. Now let's go under the hood and have a look at some components that assist us with the 12 volt battery charging system. To continue our conversation about DC to DC conversion, I've brought everyone back out underneath the hood of our Nissan Leaf. Since I mentioned before, DC to DC conversion is primarily happening to charge the 12 volt battery. But the computer, the VCM, needs a lot of information about the state of this battery. So if we look at the negative side of the battery cable, we're going to find a 4-pin connector that connects to a sensor that's right on the negative side of the battery. This sensor is a temperature sensor and a current sensor. And it's going to send these 2 data inputs directly to the VCM, and the VCM is going to analyze all the systems that are operating in the car and the state of health of this battery, and then it's going to make a command to the power delivery module, the PDM, which is the main powertrain unit for the vehicle. It's going to make that command to see whether or not we need to increase the amount of DC to DC conversion, which will increase the amount of output, or whether we need to decrease that if our battery is charged up enough, because we certainly don't want to overcharge our battery. So we're going to go right back to the scan tool and we're going to look at those data points together. So I've added a couple more data points to our custom data list. We're still working on the Nissan Leaf in the EV HV vehicle control menu. If you see in the top left hand corner, that's our battery current average. That's is a input that we're receiving directly off the negative side of that battery cable. And then the second point down on the right is your 12-volt battery temp. That's also another input that we're receiving from the sensor that we just looked at. In the bottom left-hand corner, we see our DC to DC converter request voltage. So this is going to be what the VCM is requesting the DC to DC converter to output. And then we can see on the other side, the 12-volt battery voltage is about 12.96 or so. So we're pretty close here between actual battery voltage and DC to DC request voltage. And that's what we want to see. We don't want to see a large difference between these two. That would be an indicator that maybe we have a bad 12-volt battery or possibly an issue with our DC to DC converter in the PDM. So just wanted to give you a highlight of some of these different data points because, again, it's excellent to expose your students to this type of information because these are going to be data points that technicians are going to be looking at when they're trying to diagnose either a vehicle that won't ready up or a vehicle that's got trouble codes related to the low voltage battery system or DC to DC converter codes as well. So we've been previously discussing the DC to DC conversion, which was found inside the power module and the traction motor. They're all built together on the Nissan Leaf that we've been looking at. We want to take this thing to the next step where we're going to talk about the DC to AC inverter. And on our electric vehicle systems trainer, we do have our DC to AC inverter. I'm going to give you a basic rundown of what's going on here. So we've got our high voltage battery pack here going through our circuit protection. We're going to be activated by the high voltage contactor. That's activated by us readying up on this switch over there. Once our contactor is closed, then power is supplied to the DC to DC converter, and also high voltage is supplied to the DC to AC inverter. This unit usually has two main functions. One is it takes the high voltage DC power that comes out of the battery pack and converts it, or I should say inverts it, into a AC signal. This particular unit converts 24 volts on this side to 120 volt AC at 60 hertz on this side. We're getting a nice AC sine wave that comes out that's going to drive our permanent magnet synchronous AC traction motor that we've got right here. So this is basically a very, very small version of what we would find inside of this Nissan Leaf or other potential electric vehicles that are out there on the market. Now, I do want to preference that not all the electric vehicles run AC motors, but it seems that a large majority of them do. But it is possible that they can do some DC motor control through the inverter. So the inverter, step one was to invert the DC to AC. Step two is it's going to actually control the traction motor itself. So the inverter gets signals from the vehicle control module, and those signals are interpreted to determine how much torque and power to apply to the traction motor. So two main purposes inside of this unit: taking DC, inverting it to AC, and then supplying the correct amount of power at the correct phase to the AC traction motor based upon all of your customer inputs. So we're going to head back over to the Nissan Leaf and we're going to check out where this inverter's at on the car. The DC to AC inverter can be found inside the power delivery module, or sometimes we like to refer to it as just the electric powertrain unit. This is the big unit that we see underneath the hood of this particular vehicle here. And there's a lot of the critical systems are included, all stacked together inside of this unit. At the bottom and kind of off to the side is going to be your traction motor with your gear reduction. We're also going to have our DC to DC conversion going on in there, as well as that DC to AC inversion, as well as all of the actual control features necessary to control that power delivered to the traction motor itself. Unfortunately, due to the high voltage situation that's underneath of all this, it's going to be almost impossible for us to do any actual testing or diagnosis outside of things like voltage leakage or actually doing some winding testings on the inverter, or I'm sorry, on the traction motor coils as well. So in order to get a better look at what's going on here and a better understanding, I do recommend that you encourage your students to get their scan tool out and look at the data points that are available. So let's go ahead and check out a few ourselves. We brought out our 4-channel lab scope. We've got a couple of lines hooked up to our 5820 EV trainer here. I've got 2 different traces running on our screen, and what you would want to do with this is, first of all, you can never do this on an actual EV car. The amount of AC voltage and DC voltage that are produced by the battery pack and the inverter assembly will supersede everything that your lab scope's capable of handling. But because we use a scaled down model for the trainer itself, you can actually allow your students to use traditional automotive tools and diagnostic equipment to try to get a better or a further understanding about what's really going on inside the AC to DC inverter. And with that being said, let's take a quicker look at our lab scope here and let's see what our readings are looking like. So if you notice, I have 2 traces up here. I've got a yellow trace, it's on a 50 volt scale, and then I have a green trace, it's on a 200 volt scale. So if you'll notice, you've got the nice flat line running right under 25 here. That's representing and tied into or tapped into our high voltage output of about 24 volts. And if you were looking directly at the board, you would be able to see, read that voltage off the DC to DC converter, because we do have a voltage output display on that. And then on the output side of the inverter is going to be our green trace. And remember, our green trace is running just above 60 volts and then down here to just about 60 volts on the other side, giving us a 120 volt swing, 60 volts to the positive, 60 volts back to the negative, and we have a beautiful sine wave that's created. And I think this will really help your students have a better understanding about what's going on within the system, and that's going to, allow them to better visualize that, hey, in the inverter, we're taking a flat line DC voltage, we're recreating and simulating a AC signal coming out. Now, it is important that you express to your students that in an actual EV car, that this is going to be a 3-phase AC signal, which is the same thing as what we see up here in the green trace, but it's just going to be times 3, and then they're going to be phased out correctly so that way they can have proper motor control. So we're looking at the electric motor control data list for the 2013 Nissan Leaf. I've got some data parameters pulled up. These are ones that I would recommend that you expose your students to give them an introductory to what's really going on with that DC to AC inverter. So there's a few things that we want to look at here on this list. I'm going to start in the top left-hand corner. That you're going to see our command torque. What that number is, that displays the torque command value from the computer via the CAN network. So basically, when you hit the gas pedal, you're making a request to the computer, and that request to the computer is going to translate that into an approximation of needed torque, and then it's going to apply power accordingly through the inverter. Underneath of that, still remaining on the left-hand side, we're going to see our 12-volt power voltage. So that's just a readout right off the battery to let us know what our auxiliary battery looks like. Motor speed's pretty self-explanatory. It's going to tell you the RPM that the electric motor is running. Underneath of that, we're going to see carrier frequency. So the DC to AC inverter does output its power at 5K. Now that is variable, so when the power needs to be reduced during high temperature situations, or if you've been really pulling a lot of heavy grade or have a larger payload in the vehicle, it can reduce that carrier frequency, but its standard is 5,000. Underneath of that is we got our shift position. As we can see, we're in park right now, which is why our command torque is 0. Underneath of that, we've got our output limit inverter temperature. Now, the output limit inverter temperature displays the output limit, and the output limit is really based upon all of the previous history of the motor inverter operation. So if there's incredible amounts of temperature increase, then we can go into a limit mode. So you can see here right now the output limit of the inverter temp, that it is active and that it is limiting based upon its previous exposure out there. Now we're moving to the right-hand side column. We see our motor temperature. So that's a monitored number for our output limits, as we'll see as we get towards the bottom. Underneath of that, this is one of the most critical points. This is our inverter input high voltage. So this displays how much voltage is actually coming out of the traction, out of the lithium ion battery pack and being received by the DC to AC inverter. So it's very important that this number remains somewhere in an appropriate range of the repair manual. When you look at the Nissan Leaf, they say it's about a 300 to 400 volt system here. So with 394, we're right at the upper end of that level. Underneath of that is we see our sequence mode. So this is going to be an input from the resolver. Underneath that, there's our charge relay. We already talked about charge relays and it's already activated. We can see that it's on there. We do have a simple supply or high voltage supply data line. It just basically lets us know whether or not there is high voltage present within the system here. And then at the bottom, again, we have our output limit motor temperature. So if the motor has been experiencing a higher temperature than what the computer wants to allow, it will actually limit the amount of power being driven through it as a safety precaution so you don't burn up your motor. So to kind of let's change some of this data points up. What we're going to do is we're going to put our vehicle in drive here. So we're going to be able to watch this in the bottom left-hand corner. Our shift position is going to change from park to drive. So let's go ahead and do that. And then we're going to see our command torque. It did change a little bit there. If we leave our foot on the brake pedal and just press the gas pedal just a little bit, we're going to see that command torque number come on. There we go. Now we see that torque number come up. And now we're just going to let off everything. We're going to put it back in park. And so now we do that so we can see that the command torque is actually happening, that we're got, command coming from our accelerator pedal through the VCM that's being controlled to the inverter to command that amount of torque necessary. So these are some excellent introductory PID data. Now there's obviously a lot more that we can look at here, but these are great ways to introduce your students to inverter operation and what type of information they should be seeking out on the scan tool to perform any troubleshooting. So with that being said, we're going to go forward and we're going to start looking at our lithium-ion batteries. Before we look at some troubleshooting techniques on the electric vehicle, I want to take a moment to talk about the lithium-ion battery pack. Typically, most electric vehicles are using some sort of solid-state battery or lithium-based battery pack, and there are some concerns for overheating or the battery's getting too cold. There's some charge concerns. There's a lot of unstable things about lithium-ion batteries that need a complicated computer control system to ensure that everything remains safe. On our 5820 board, we do have a simulated high voltage battery pack, but our battery chemistry in this battery is nickel metal hydride. It is comprised of 20 different cells that produce about 1.2 volts, and each cell has about 2200 milliamp hours of capacity. So the combination of all these different cells stacks up in order to get our total high voltage output, and then our milliamp hours is basically going to be how long we can actually use this battery given a certain amount of current draw on it. If you also notice on top, we have a stated charge indicator. So by simply pressing a button here, we can get an immediate stated charge of our of our high voltage battery. Notice we're running about 50% right now, so we have been running this unit quite a bit today. Also built into this unit is a temperature sensor, so if the battery pack was to get too hot during the charging process, it will actually stop the charging process completely to prevent any damage happening from the batteries, the cells, or to the trainer itself. Couple things we want to mention that this is different than the battery we're going to be looking at on the Leaf. The battery on the Leaf is a lithium-ion based. It has 192 cells and produces approximately 360 volts and has a capacity of about 24 kilowatt hours. So it is a substantially larger, beefier, and more powerful battery pack than what's on our simulator. But notice we don't have to wear any special gloves. Everything is very safe to work on here. If we wanted to work on the lithium-ion battery pack, we would definitely need to be wearing all of our proper safety PPE in order to do some exploration. One other additional component that I do want to mention is inside of the Leaf's lithium-ion battery pack is a lithium-ion battery controller. Due to the sophistication of this unit, it does need a computer that is installed directly into the battery pack near one of the module stacks. And the lithium battery controller is the core of the battery control. It detects the voltage and current of the assembled battery. It detects the temperature of each module and the voltage of each cell to judge the state of charge. It also calculates the possible input-output values. It meters indication values and also chargeable values, and sends all this data to the VCM, or the vehicle control module, and then that module controls the vehicle according to the battery state. So you got a lot of sophistication going on in here. In order to kind of break that down into a more simplified manner, we're going to slide over and take a look at some live data off of our Nissan Leaf. So we have our high voltage battery data parameters pulled up. There are over 100 different PID datas for this particular system. I've only pulled up a select few. If we look here at the top, we see battery temperatures 1 and 2 and battery temperature 4. So I just picked 3. We're monitoring battery temperature all over the system, looking for any indications of overheating, or if the battery is too cold, then it may not charge correctly. So just like our trainer, the Nissan Leaf has several battery temperature sensors built in, and you can read those values directly off of the scan tool like we're looking at here. Since this vehicle's been sitting in our shop overnight, the battery temperature should be very, very close to what ambient air temperature is. So if you've got a electric vehicle in, it's cold soaked in your shop all night, and you come out and your battery temperatures are not close to the ambient air temperature, it's possible that you have a battery temperature sensor concern. Second down on the right hand side column, we see our total battery voltage. We see that is 394.5-ish volts. This is showing us that we are very, very much at the top end of what our rated voltage is for our battery. So it appears like our battery's in pretty good shape here. Underneath of that and sprinkled out, we're going to see some different cell voltage readings. Again, there are over 192 cells, and each one has its own data line here. So I just pulled some random ones up to show you. And really what I would be looking for as a technician is I want to see that all my cell voltage numbers are all very, very close to each other. If I have any that are leaning way high or way low, then that might indicate either an issue of the cell or an issue inside that particular stack where that cell exists. Another two important data points I want to point out is the maximum cell voltage line and the minimum cell voltage line. So these are going to be your numbers where, you know, this is where the computer's recording the maximum amount of cell voltage that's there and the minimum amount of cell voltage that's there. And you would use these two lines to make a determination if you need to do a module charge balance, which would be like pulling the battery out and pulling each individual cell stack out. Maybe if you're trying to just make a repair on one specific cell, you're going to want to capture these data points prior to pulling the battery out, so that way you'll have this information to input into your module charge balancer if that's something that you need to do. Other things that I left on here is the service plug interlock. I can't tell you how many EV and HEV cars I've had come back from body shops where the service plug interlock was not properly installed, not properly latched all the way. A lot of them have multiple safety latches on them. Some of them just simply are just forgotten to be put in. But I always include that data point in there, because if the service plug is not in there, we'll get no power up to the power module itself. You know, that is the main gateway between the battery pack and the power delivery module. So it's always important to show your students that they need to be mindful that it seems very simple, but it's definitely something that we want to take in consideration when we're looking at our high voltage battery. So again, just some basic information here. We don't have to open the different stacks up. This is pretty involved with the Nissan Leaf as far as dropping the entire belly pan out. You have to use a windshield removal tool to split the case in half, and then once the case, because it's all waterproof because it lives under the car, once the case is split in half, then you'll get access to the different cell stacks. But that's a tremendous amount of labor, so I think it's important that we teach our students that they can get a lot of great information just sitting in the driver's seat in their car, evaluating data items like we're showing here on the screen. Now we're going to go ahead and we're going to move forward with some diagnostic work and see if we can do some troubleshooting on our Nissan Leaf. We're inside our vehicle technology trainer, and we're going to show off some of the faulting capabilities of this unit. If you see in this box here to my right, We've got our ATEC installed fault box, and this all comes pre-wired for you as the instructor to utilize during your class to help your future technicians dial in on their troubleshooting and diagnostic skills. It works pretty simple. There's a switch in the top right hand corner. We turn that on. That lights the fault box up. We have a wide variety of potential faulting. On our top left, we have what we call our variable faults. So these are going to be faults on your accelerator pedal position, your battery current sensor, your AC power circuits, and your coolant temperature sensor circuits. Then underneath that, we have our hard faults, which are going to be our open faults. They're going to be on occupant detection, tire pressure monitoring, stop lamp switch, your CAN low signal, your ignition switch, and your drive motor A. So it's really neat how this works. What you do is, once you're inside, if you have a voltmeter right here, and you can select on any option that you want, and that's going to give you the voltage reading on the faulted wire. So right now we've got our accelerator pedal pulled up, and my foot's off the pedal, and I'm reading about 0.8 volts. And if I put my foot on the pedal, it brings my number up to about 4.66 volts. That's about accurate for what you're going to see on the data list on the scan tool. When I activate this fault, what's going to happen here is the fault box is going to take over the signal sent to the computer, and then you could use this potentiometer to dial in the amount of voltage that you'd actually like to see on that wire. If we dial it all the way down to 0, then that's going to be almost like an open. And then if I bring it all the way the other direction, I'm going to be almost at 5 volts. It's going to be like I've got the pedal pressed almost all the way to the ground. Or you can leave it somewhere in between. But the number's going to be stagnant, and I'm pressing on the pedal. It does not respond. So that's how the fault box works. Once this happens, then this is going to set a code in the vehicle, and we're going to go ahead and switch over to the scan tool and see what that looks like there. And we're in a quick diagnostic check of the EV/HV vehicle control computer. Notice that our fault box, due to the situation it's created in the circuitry, has set 3 different codes: a P2122, a P2123, and a P2138. And at this point, you could dive right into what the repair manual wants you to do, but I always recommend and try to steer my students towards actually checking out the live data first before we start getting our DVOM out and making some voltage measurements. So I'm going to switch over real quick, and we're going to take a look at the live data. We got the live data list pulled up here, displaying accelerator pedal position number 1 and accelerator pedal position number 2. Typically, when you're looking at these data points, they should be close to each other, but never the same, and they should not be 0 volts and they should not be 5 volts. We can immediately tell that there's a pretty drastic difference between sensor number 1 and sensor number 2, meaning that number 1 sensor is reading about 3.6 volts and sensor number 2 is reading about 0.7 volts. If I go ahead and press my foot down on the gas pedal, we're going to watch and see accelerator pedal position number 2 moved up to about 2 volts, while accelerator pedal position number 1, that voltage has remained the same. So when I take my foot back off the pedal, we'll see sensor number 2 appears to be operating properly, but sensor number 1 is stagnant with about a 3.6 volt reading on it. This is a great indicator for your technicians. That way they know that the problem was with the sensor wire on number 1. And the 3.6 volts that we're seeing on there is what we've dialed in on the fault box. So the voltmeter that's in the fault box, the readout on it should match this parameter data on display for accelerator pedal number 1. These are going to be great ways to start your students off with their diagnostic strategies. We use more scan tool use now than we ever have, so it's very important to get them used to looking at this data and analyze what's going on before they pull out their voltmeter and take some measurements. Now that your students have analyzed both the diagnostic trouble codes and the live data available for them, now would be a great time for them to research that code in the repair manual and follow the diagnostic trouble tree to take the additional measurements necessary to pinpoint exactly where the problem is. You as the instructor already know where the problem is and what the value should be because it's already displayed here on the voltmeter for you, and you already know what circuit has been faulted. The other nice part about this box is it does close and it does lock, so that keeps everybody out of here and they can't see what faults you've done on the vehicle itself. So this makes for a great troubleshooting exercise for your students and a great way to integrate this into your training program. I hope you've enjoyed today's training video. We certainly have covered a lot. from charging EVs all the way down to analyzing EV systems and doing some electric vehicle troubleshooting. Hopefully you can use this material in your training program or to use with your students to help make them become better electric vehicle technicians. If you've enjoyed today's training video, be sure to check us out on YouTube and our entire content library. Also, please see our social media pages on Facebook and LinkedIn. Give us a like and let us know that you're out there watching. Thanks a lot, and we'll see you next time.